Listen to this. There's a black hole out there, sitting in the heart of the Perseus galaxy cluster, about 250 million light years from Earth. And it's singing, not metaphorically, not in some poetic sense, actually producing sound waves that have been rippling through space for 2.5 billion years. When scientists at NASA first detected this in 2003 using the Chandra X-ray Observatory, they thought their instruments had malfunctioned. Because what they were seeing shouldn't have been possible, the note is a beef, lat, but here's where it gets truly mind-bending. This beef, lat, is 57 octaves below middle C. To put that in perspective, a piano has 7 octaves. The deepest note a human ear can perceive is maybe 20 hertz. This cosmic note, it vibrates once every 10 million years. It's a million billion times deeper than anything we could ever hope to hear. If you could somehow amplify it enough for human ears, it would be less like music and more like the fundamental heartbeat of the universe itself. Now, you might be wondering how sound can exist in space at all. We've all heard that in space, no one can hear you scream, right? That's true in the vacuum between stars, but galaxy clusters aren't empty. They're filled with hot gas, tenuous but present, providing a medium for sound waves to travel through. The black hole at the center of Perseus is supermassive, containing the mass of millions or billions of suns compressed into an infinitesimally small point. As matter spirals into it, the black hole doesn't just swallow everything quietly. It releases enormous amounts of energy. This energy creates pressure waves that push through the surrounding gas like ripples on a pond. Except these ripples are tens of thousands of light years across. The really shocking part isn't just that black holes make sound. It's what this sound does. These pressure waves are actively shaping the galaxy cluster. The gas surrounding the black hole should be cooling down, collapsing under its own gravity, and forming new generations of stars. But it isn't. The sound waves are keeping the gas hot, preventing it from condensing. The black hole is essentially conducting a cosmic thermostat, regulating star formation across thousands of light years through nothing but sound. It's using acoustic energy to sculpt entire galaxies. Think about what this means for our understanding of the universe. For decades, we thought black holes were relatively simple objects. They pull things in, they emit radiation, end of story. But they're actually far more active participants in cosmic evolution than anyone imagined. They're not cosmic vacuum cleaners sitting passively at galactic centers. They're more like cosmic engineers, using sound as a tool to control their environments over billions of years. Scientists have since discovered similar acoustic phenomena around other black holes. This isn't a unique occurrence. It's a fundamental mechanism by which supermassive black holes interact with their host galaxies. The universe is filled with this inaudible symphony, with black holes humming their deep notes across the cosmos, shaping the very structure of space through sound waves that have been traveling since before Earth even existed. We live in a universe that literally hums with the voices of black holes. And we only just learned to listen. Picture Earth from space, that blue marble covered in oceans that make up 71% of its surface. For most of human history, we thought this was special. We assumed water was rare, that our planet occupied some privileged position in the cosmos where conditions were just right for liquid water to exist. We built entire frameworks of planetary science around the idea that Earth was unique. Then we started looking closer at our own cosmic neighborhood, and everything we thought we knew shattered. Europa, one of Jupiter's moons, has twice as much water as all of Earth's oceans combined. Let that sink in. This moon, which you could fit inside our own moon several times over, contains more water than our entire planet. It's locked beneath a shell of ice, but it's there. An entire subsurface ocean, kept liquid by tidal forces from Jupiter's immense gravity, possibly hundreds of kilometers deep. Scientists didn't expect this. They couldn't have predicted it based on our old models of how solar systems work. Then there's Enceladus, a tiny moon of Saturn barely 500 kilometers across. NASA's Cassini spacecraft flew through geysers of water erupting from its south pole, shooting hundreds of kilometers into space. These aren't small fountains. They're massive plumes containing organic molecules, salt, and silica particles, suggesting hydrothermal activity on the ocean floor. An alien ocean with underwater volcanic vents, just like the ones on Earth where life might have first emerged billions of years ago. But the discoveries didn't stop at moons. Astronomers found water vapor in the atmospheres of exoplanets orbiting distant stars. They detected water molecules locked inside asteroids, suggesting that Earth's oceans might have been delivered by cosmic collisions billions of years ago. They even found water in the sun itself, broken down into hydrogen and oxygen in certain cooler regions of the solar atmosphere. Water isn't rare, it's everywhere. The implications are staggering. For decades, the search for extraterrestrial life focused on finding planets in the habitable zone, that narrow band around a star where water could remain liquid on the surface. We thought we were looking for Earth's twins. Now we realize we were thinking too small. Moons orbiting gas giants far beyond the habitable zone could harbor life. Rogue planets wandering through interstellar space could have subsurface oceans kept warm by internal heat. Even comets and asteroids might contain the chemistry necessary for life. Scientists estimate there could be more water in the outer solar system alone than in all of Earth's oceans. Multiply that by the billions of star systems in our galaxy, and you're looking at an almost incomprehensible abundance of water scattered throughout the cosmos. The universe is awash in the very substance we consider essential for life. This discovery fundamentally transformed astrobiology. We're no longer asking if water exists elsewhere. We're asking where it doesn't exist. Every new telescope, every new mission reveals more water in more unexpected places. The universe isn't a desert with rare oases. It's an ocean with scattered islands. And if water is this common, if the primary ingredient for life, as we know it, pervades the cosmos, then perhaps we're not alone. Perhaps we never were. Imagine throwing a ball into the air. Gravity pulls it back down. That's how we thought the universe worked on the largest scale. The Big Bang threw everything outward, and gravity should be slowing that expansion down, eventually maybe even pulling everything back together in a big crunch. Simple physics, logical, wrong. In 1998, two independent teams of astronomers were racing to measure exactly how much the universe's expansion was slowing down. They were studying Type Ia supernova, exploding stars that shine with predictable brightness, making them perfect cosmic yardsticks for measuring vast distances. They expected to calculate the deceleration rate, refine our models, maybe win some awards. Instead, they found something that made no sense whatsoever. The universe wasn't slowing down, it was speeding up. The data showed that distant supernovae were dimmer than they should be, meaning they were farther away than expected. Galaxies weren't just moving apart. They were accelerating away from each other, pushed by some unknown force that overpowered gravity itself. The astronomers checked their calculations dozens of times, convinced they'd made an error. They hadn't. The universe was running away from itself, faster and faster with each passing moment. Scientists had no framework for this. Nothing in physics predicted it. They scrambled for explanations and eventually landed on a term: dark energy. But don't let the name fool you. It's not really a discovery. It's a label for our profound ignorance. We have no idea what dark energy actually is. We just know it's there because we can measure its effects. And here's the truly shocking part. This mysterious force comprises 68% of the entire universe. More than 2/3 of everything that exists is something we cannot see, cannot touch, cannot understand, and have no theory to explain. Think about living your entire life in a house, believing you know every room, every corner. Then one day you discover that most of the house consists of spaces you didn't know existed, filled with something you can't perceive. That's where we are right now with cosmology. We've mapped galaxies, calculated the masses of stars, traced the history of the universe back to fractions of a second after the Big Bang. And yet, the dominant component of reality is completely unknown to us. The consequences are profound. If dark energy continues pushing at its current rate, the universe will expand forever, eventually tearing apart galaxy clusters, then galaxies themselves, then solar systems, potentially even atoms, in what scientists call the Big Rip. Or maybe dark energy will change strength over time in ways we can't predict. We simply don't know. Our equations work, our predictions match observations, but we have no physical understanding of what's actually happening. This discovery earned a Nobel Prize in 2011, but it didn't provide answers. It opened a chasm in our understanding of physics. Somewhere in the nature of space itself, in the quantum foam of reality, or in dimensions we haven't discovered yet, lies an explanation for why the universe is accelerating into an ever-expanding future. Until we find it, we're living in a cosmos where the majority remains a complete mystery. Every planet we've ever studied orbits a star. Mercury circles the Sun. Jupiter dominates its solar system, but still dances around our star's gravity. The thousands of exoplanets we've discovered all follow the same pattern, locked in orbital embrace with their parent stars. This seemed like a fundamental rule of planetary existence. Planets need stars. They form from the debris disks around young stars. They're heated by stellar radiation. They're defined by their relationship to the light at the center of their system. Except that's not true at all. Floating through the darkness between stars are rogue planets, worlds without suns. Some are gas giants larger than Jupiter. Others are rocky bodies similar to Earth, all wandering through interstellar space completely alone. They were either ejected from their birth systems through violent gravitational interactions with other planets, or they formed independently in the depths of space, condensing from clouds of gas and dust without ever being captured by a star's gravity. And here's what shattered every assumption scientists had. These orphan worlds might outnumber stars in our galaxy. Let that sink in. For every single point of light you see in the night sky, there could be multiple planets drifting invisibly through the cosmic void. The Milky Way contains roughly 200 to 400 billion stars. If rogue planets outnumber them, we're talking about potentially trillions of hidden worlds that we never knew existed. The galaxy isn't what we thought. It's not just stars with their planetary families arranged in neat systems. It's a sea of darkness filled with invisible wanderers. Scientists first detected these rogue planets through gravitational microlensing, a technique where a planet's gravity briefly magnifies the light from a more distant star as it passes in front. The calculations suggested there could be twice as many rogue planets as stars, possibly more. Some estimates push that number even higher. We're still refining our detection methods, still discovering more, and every new survey suggests the universe is stranger and more crowded than we imagined. Now think about what this means for life. A planet without a star sounds like the coldest, deadliest place imaginable. No sunlight, no warmth, just eternal darkness as it drifts through space for billions of years. But some of these rogue planets could be massive enough to retain thick atmospheres that trap internal heat. Others might have subsurface oceans kept liquid by radioactive decay in their cores, similar to Europa, but without needing Jupiter's tidal heating. They could have ice shells kilometers thick, protecting potential ecosystems from the cold of space. Life, if it exists on these worlds, would be utterly alien, evolving in complete darkness, powered by chemistry rather than photosynthesis. We've spent decades searching for habitable planets around other stars, building telescopes to find Earth, like worlds in Goldilocks zones. Meanwhile, an entire hidden population of planets has been passing through our galaxy unnoticed. We can't see them. We can barely detect them, but they're there, possibly in numbers that dwarf everything we can see in the night sky. The universe has a shadow population, invisible wanderers carrying untold stories through the darkness, and we've only just begun to realize they exist. We measure our lives in seconds, minutes, hours. We synchronize our watches, set our clocks, and assume that time flows uniformly for everyone, everywhere. It's one of the few things that seems absolute, unchanging, fundamental to existence itself, except it isn't. Time is flexible, malleable, and it moves at different rates depending on where you are in the universe and how fast you're moving. Einstein predicted this over a century ago, but actually measuring it, actually watching time bend and stretch in real-world conditions, still leaves scientists stunned. Astronauts aboard the International Space Station age faster than people on Earth. Not by much, about 0.07 seconds over 6 months, but measurably, verifiably faster. They're moving at roughly 28.000 kilometers per hour and experiencing slightly weaker gravity than we do on the surface. Both factors affect how time passes for them. When they return to Earth, they've literally traveled into our future, even if only by fractions of a second. Their clocks, their cells, their entire existence has moved through time at a different rate than ours. GPS satellites have to account for this constantly. They orbit about 20.000 kilometers above Earth, where gravity is weaker, making their clocks run faster than clocks on the ground by about 45 microseconds per day. But they're also moving at high speeds, which makes their clocks run slower by about 7 microseconds per day. The net effect is about 38 microseconds faster per day. That doesn't sound like much, but GPS depends on nanosecond precision. Without correcting for time dilation, your navigation would be off by kilometers within hours, miles within a day. Every time you use GPS to drive somewhere, you're relying on Einstein's equations about the flexibility of time. Near black holes, time nearly stops relative to distant observers. If you could somehow survive approaching the event horizon of a supermassive black hole and hover there for what feels like an hour, then escape back to Earth, you might find that thousands or millions of years have passed. Your family would be gone. Your civilization might be gone. Entire species could have evolved and gone extinct while you experienced 60 minutes. This isn't speculation or theory. This is confirmed physics, mathematically certain, demonstrated through countless experiments and observations. Gravitational waves, those ripples in spacetime caused by colliding black holes and neutron stars, are literally distortions in time itself moving through the universe at the speed of light. When LIGO detected them in 2015, it wasn't just detecting movement in space. It was detecting the stretching and compression of time, watching as the fabric of reality itself oscillated. The universe doesn't have a universal clock. There's no cosmic standard that everything syncs to. Time is local, personal, dependent on your velocity and the strength of gravity around you. Two observers in different parts of the universe, experiencing different gravitational fields, are literally existing in different time streams. The present moment isn't the same everywhere. The universe is a tapestry where time moves at different speeds in different regions, where past and future blur depending on perspective. We live in a cosmos where time itself is negotiable. Deep inside Neptune and Uranus, something extraordinary happens that sounds like pure fantasy. The atmospheric pressure becomes so crushing, so impossibly intense, that it literally tears apart methane molecules floating in those alien skies. The carbon atoms, freed from their hydrogen bonds, get compressed under thousands of times Earth's atmospheric pressure. And they crystallize, they form diamonds, not small diamonds, not tiny specks. We're talking about chunks that could be millions of carats, each one potentially the size of your fist or larger, falling slowly through layers of liquid metallic hydrogen and helium like hailstones in a storm, except this storm has been raging for billions of years, deep within planets where no human will ever witness it. Scientists didn't just theorize this, they tested it. Researchers used some of the most powerful lasers on Earth to recreate the extreme conditions inside ice giants. They blasted polystyrene with intense pulses of energy, generating pressures over 1,000,000 times Earth's atmosphere and temperatures of several thousand degrees. The carbon atoms in the plastic compressed into diamonds right before their instruments, not just possible, probable, happening right now on worlds in our own solar system. Imagine descending through Neptune's atmosphere in some impossible spacecraft. You'd pass through layers of hydrogen, helium, and methane. Deeper still, the pressure would mount until you entered a region where diamonds drift past your windows like snow, some tumbling slowly, others shooting downward toward the planet's core. Eventually, these diamonds might accumulate in massive layers around the core itself, creating diamond oceans or even a solid diamond core at the planet's center. This discovery revolutionized planetary science, showing us that the universe creates treasures in the most hostile environments imaginable. What we consider precious and rare on Earth falls like rain on distant worlds. The cosmos operates on scales of abundance and strangeness that dwarf human imagination, performing alchemy through nothing but pressure and time. In 2007, an astronomer named Duncan Lorimer was sifting through old radio telescope data from observations made 6 years earlier. He found something that shouldn't exist, a burst of radio waves so brief it lasted just 5 milliseconds, but so powerful it released as much energy as the sun produces in an entire day. Not a week, not a month, a single day's worth of solar output, compressed into a blink that lasted less time than it takes to snap your fingers. And it came from a galaxy billions of light, years away. At first, everyone assumed it was a mistake. Maybe interference from a microwave oven in the observatory, maybe a satellite passing overhead, maybe corrupted data. Radio telescopes pick up interference constantly, and extraordinary claims require extraordinary evidence. But then they found another one, and another, hundreds more. These fast radio bursts, as scientists started calling them, were real. They were coming from deep space, and nobody had any idea what was causing them. The energy involved is staggering. Whatever produces these bursts generates more power in milliseconds than our sun will produce over the course of days. The signals travel across billions of light years of space and still arrive at Earth strong enough to detect. Imagine the power source required for that. It's almost incomprehensible. Some bursts appear once and never repeat, like cosmic fireworks that flash once and disappear forever. Others repeat in patterns that scientists are still trying to decode. One repeats every 157 days like clockwork. Another fires off dozens of bursts in irregular clusters, then goes silent for months. Theories multiplied wildly. Maybe they're from magnetars, neutron stars with magnetic fields, trillions of times stronger than Earth's. Maybe they're from colliding neutron stars. Some scientists suggested they could be evidence of advanced alien civilizations using massive energy beams to power interstellar spacecraft, with Earth accidentally catching the spillover radiation. That last theory might sound like science fiction, but the honest truth is we still don't know. The mystery deepened when astronomers finally traced one burst to its source galaxy and found nothing unusual there, no obvious cataclysm or exotic object that could explain it. Then in 2020, something incredible happened. A fast radio burst erupted from within our own galaxy, originating from a known magnetar just 30 light years away. Finally, a clue. Scientists could actually study the source, measure its properties, understand the mechanism. Magnetars, those ultra-dense stellar remnants with insanely powerful magnetic fields, could definitely produce these bursts through starquakes or magnetic field reconfigurations. Mystery solved, right, except the repeating ones still don't make sense. The patterns are too regular, too structured. And the bursts from distant galaxies are far more energetic than anything the local magnetar produced. We might have found one explanation for some fast radio bursts, but others remain completely mysterious. The universe is screaming at us in radio waves, sending messages we can detect but cannot yet understand. Every answer reveals deeper questions. Every solution suggests phenomena we haven't even begun to comprehend.